Hello everybody. In this, the fifth video of the x86 hobby channel, I'll be introducing you to a small compact application written for the Linux terminal. In fact, it's a replacement for Echo and it's called Echo Wait. Again, it's written with the using the Edlinpro, and it contains the header, which will be the template, and of course it's being debugged by our built-in debugger. All these are contained in my Google Drive, the link to which you'll find in the description of the channel. As well as the binary file itself, you'll also get the source code. You can download the source code, and in this video I will be going over the source code in some detail, so you should download it and look at it whilst we're going over it if you want to follow. Okay, so let's see a little bit more about Echo Wait. Okay, what is Echo Wait? Echo Wait is a replacement for the Linux echo command. Like Echo, it displays strings following the command. However, it can display multiple strings, each on a new line. It then waits for a key to be pressed before returning. This is an important difference, and that's the reason why it's called Echo Wait and not just Echo, because it will wait for a key to be pressed before continuing. In addition, each string can be displayed either left, center or right justified. To achieve this, a number 0, 1 or 2 is placed at the start of each string. If no number is placed, then default is left justified. For example, if you were to type Echo Wait, this is left justified, this is center, this is right. Notice I put a 0 on at the front of the first string. If I'd have left it without any number, it would be by default left justified, and the result when you actually run this is this is left justified, this is center, this is right justified. Now this justification depends on the actual width of your terminal screen at the time, but this is automatically done by Echo Wait. It reads the screen dimensions automatically. In fact, this presentation itself uses Echo Wait. This whole thing is using Echo Wait. You'll have noticed that in this presentation we've got attributes as well as text, in other words color, underline, etc. To achieve this, escape sequences can be inserted in the strings to give these attributes, such as background and foreground color, underline, bold, whatever. And even you can move the cursor and clear the screen. This is also important. More precisely, a CSI or control sequence introducer can be inserted. A control sequence introducer is escape open square brackets. This is achieved by inserting a tilde in the string. A tilde is that wavy line on your keyboard. For example, Echo Wait 2 tilde 91M gives you a bright red right justified. So that string tells the Echo Wait that the string should be right justified. It should have a bright red text, the M signifying the end of that escape sequence. So what follows then, bright red, is the beginning of the actual text. Okay, so let's see how that looks. Bright red, right justified. Okay. So by using tilde, it enables you to put insert a control sequence introducer, which is actually 2 characters. It's escape open square brackets. Okay. Note in this example is expanded to that. You could get the same if you wanted to use Echo by first of all enabling it to recognize the 1B hex and then the open bracket square brackets 91M, but this is a lot more convenient by using tilde. You can find a full list of all ASCII, of all CSI attributes online. But I've provided a link in the description to this channel. If you look in the description, you'll find a link to a comprehensive list of the CSI attributes. Note, if the tilde symbol is required in a string, just use double tilde. So if you want to use tilde but you don't want it to be expanded to a CSI, then just use a double tilde. Now remember that echo wait waits for a key to be pressed after printing the appropriate strings. Now it is now possible to read that key press. Very important if you want to put this in a script. You might want to know what key was pressed. Single key, but what key was pressed. In fact, echo wait returns a number that indicates the key pressed. This is the exit code from echo wait, and it's a number between 0 and 255. All applications running in terminal will return some sort of exit code. Echo wait uses that exit code to tell you what key has been pressed. This number can be used in scripts. A very simple example would be if you use echo $, which you might be familiar with, which shows you what number has just been generated by the last echo wait. You can actually use echo wait $? As well, but I'll go to that later. This number is the ASCII value of the key pressed, ORed with hexadecimal 20. Okay, and we'll see the significance of that. Examples. The first example, y equals 121. Notice, because we ORed by 20h, capital and lowercase y is the same number. Very, very handy if you ask somebody to confirm by typing y. It doesn't matter whether they type the upper or lowercase, they'll give you the same number return. And if you understand all this, then you'll notice that enter will give you 42, spacebar 32, etc. For example, if I had echo wait, press Y to proceed, any other key quits. Gives, press Y to proceed, any other key quits. So this enables you to trap, by trapping 121 when it comes out, whether Y has been pressed or not, uppercase or lowercase. Note, the tilde1a in the second string moves the cursor up one line, since the first string ends in a line feed. All the strings, you could have as many strings as you want in the echo wait command, but all of them will automatically go on the following line. They all end up in a line feed. But I wanted in this example, even though it's right justified, I wanted it to be on the same line. So what I have to do at the beginning is to move it up by one line. The 2 of course means right justified. Okay, so that is how we can insert attributes into our echo wait strings. Okay, let's have a look at some other information about echo wait. You can force echo wait not to wait for a key press. In other words, this causes echo wait to behave more like the echo command. Simply append a 0 at the end of the command. For example, echo wait, print this line without waiting for a key press, put the 0 at the end. Gives exactly the same, only it will return immediately without waiting for a key press. Note, the exit code from this non-key wait is always a 0. Since we're not pressing a key, we don't have any number to return, so it will always be a 0. You can download the binary from the Edlinpro folder in my Google Drive, as I said at the beginning, and you can find the link in the description for this channel. After downloading, you then have to change mod the echo wait binary by making it executable. You should know that, of course, any binary file stored anywhere else other than a Linux file system, you will lose its attribute, so you have to reintroduce, and the ones we want to reintroduce here is the executable attribute, so you need to do that. And then the easiest way to use echo wait, as in any other of my examples, sudo copy echo wait to user local bin. If you copy it there, then it should be available anywhere without having to specifically specify the path to echo wait. as I've done in all my examples so far. The following is a brief description of the source code for echo wait. So if you've downloaded the source code as well, and then you can follow me on the description of the source code so you can see how we did everything. Okay, let's look more closely at the echo wait source code. As you know, the source file, which is named echowait.asm, is in the Edlinpro folder. Open in read-only with a read-only editor with line numbering enabled. This enables you to follow me on this lesson because we need the line numbers to reference the actual source code when I go through this. So you must have line numbering enabled. Whatever you do, don't change the file itself. That's why you should open it either in read-only or make sure you don't do anything with it, or you will alter the line numbering. Okay, this lists the order of the functions, basic order of the functions. Follow closely. Line 30 enables the single key keyboard read mode. This is the non-canonical keyboard mode where a single key is read rather than a string of keys terminating in an enter. My last video dealt with this, so it goes in more detail as to what this function actually is in assembler. Line 30 to 34. We need to get the terminal dimensions for the justify operations. It's important to know what the width of the height is not important, but the width of the terminal we need to know. We need to know the width so that we can know how to justify the text within the size of the terminal window. Line 35, get the number of strings or arguments on the stack in EBP. These are the arguments that are passed, if you remember, they're addresses of the strings. The very first one is the address of the name of the file itself that you typed on the command line. Everything else typed on the command line has an argument on the stack. And so the number of arguments, not the arguments itself, the number of arguments I'm placing in EBP. Line 93. Set the output buffer address in EDI. Now loop until all strings have been processed. That is until EBP goes to 0. Once all strings have been processed, we move on to part 2, or the second part of our process. Line 39. Get the next string address from the stack in ESI. So ESI contains the address of the actual string, and wherever that is, we're not interested as long as we've got it in ESI. And basically we need to transfer what that string is down to the output buffer at EDI. So we've got to transfer it from ESI to EDI. But it's not a straight transfer, we need to examine carefully what it is we're transferring. Line 41. Now here we read the terminal width in ECX. We have to do this every time because we're using ECX for other things as well. So remember, we got the terminal width and it's actually in BSS space, and so we've got to read that into ECX. We have to then push the justify byte on the stack. The justify byte is the very first byte of the string. If you remember, it's either a 0, 1 or 2, or if there's no 0, 1 or 2, then by default it pushes a 0 on the stack. Now the reason why we're pushing it on the stack is we've got no more registers to hold it, so that's what we do. Line 49 to 50, we move EDX1, or since EAX is normalized, EDX just by doing CDQ and increment EDX, a 2-byte operation to move EDX1. This is used for justifying the cursor moves, as we'll see later. Also, part of the justify and the escape sequence out of justification is moving hexadecimal FF. This is to make it out of range for the reset of the justify count. Now all this sounds a little bit confusing, but in fact what we're doing here we need to know how many characters we're printing out before we know how far along to push the cursor along to the right in order to start printing. And that's where ECX comes in, as we'll see. Okay, next. Read the next string character and finish on a null. So we load string byte, read that character and finish on a null. If it's null, if there's a 0 in it, we finish. We go on to the next part of the process. If it isn't, store the character in the output buffer. Store string byte. However, we now need to track whether we have a single tilde character or a double tilde character. And if we have a single tilde character, we need to replace it with escape 1BH, which is hexadecimal 5B1B, or escape open square brackets. Line 65. Now we're going to make EDX 0 here, so that we suspend just adjusting ECX whilst in the escape sequence. It's important to know that if we're in an escape sequence, that does not count to the number of characters seen on the screen. So hence we need to skip those during the escape sequences. So we make EDX 0. And we need to adjust now ECX and loop back to reset AH and EDX if at the end of a sequence. So if we are at the end of a sequence, then the character that we've just printed is lower in value, byte value, than in AH. And if it is lower, then that means we loop back and reset everything, because now we're going to start counting again, incrementing EDX and setting AH to FF. And then we loop back anyway, but we don't loop back to reset, we loop back to the normal loop back position for the next character to be read. Now, after we've completed all that, 71 to 72, we append the reset attributes and a line feed to the output buffer. The reset attributes means we're at the end of the string, so we reset any attributes that have been set automatically, and we append a line feed. Remember, every string has a line feed at the end of it. This is where we append it, that's where it goes. Altogether, the reset attributes and line feed is only actually 4 bytes in size. So we can do a store string double there. Now we adjust ECX for justification according to AL from the stack. What we need to do now is try to insert cursor movements. If we're left justified, we don't have any cursor movements. If we're center justified, if we're right justified, we insert all the excuse me, movements that we have calculated in ECX. If we're center justified, we insert exactly half of those. And that's exactly what we do between 80 and 86. We're inserting those moves. Now we can output to standard output the whole string. So we've already moved the cursor and now we're going to move the string, including the escape sequences if necessary. Now here we're going to skip waiting for a key press if the output is only 4 bytes. Now if you remember, if we want to skip waiting for a key press, we put a 0. Now that's another string essentially, and what that tells the system, our program here, if you follow it, it means it's left justified. Okay, well we skip that, that's okay, but then we come immediately to a null. That's all there is. And then what do? We put 4 bytes at the end. Okay, well that means we don't have any string at all. So if it's only 4 bytes, if the length of the string is only 4 bytes, then that means we skip waiting for a key press. But assuming we have a string, then we wait for and collect the key press in the buffer. Now then we push on the stack the key valued ORed with hex 20H as explained previously. Now we set the keyboard to normal mode. Remember, we can call the same subroutine to achieve this, and then we quit the program with the exit number in EBX.